So good afternoon, everyone. My name is Laure Navarro. I'm very glad to be here today, especially because I graduated from UT 15 years ago. Looks like yesterday. So it's a real pleasure for me to be back on campus today and to have some of my former professors in the audience. So I'll be talking about the ITER project today. I'll start showing you what fusion is and what a fusion reactor looks like. And then I'll give a few examples on how we use 4D and photogrammetry on the project. So as Andy said, ITER stands for International Thermonuclear Experimental Reactor. So you have a multiple choice questionnaire here. It's a multinational scientific collaboration project. It's a large-scale experiment to demonstrate the feasibility of fusion energy. It's the world's largest tokamak. I'll explain what a tokamak is in a few minutes. And actually, it's all of the above. So we are located in the south of France. It's in Provence. If you want to visit, that's a nice region. And I've put here a sketch of what a tokamak looks like. So I don't know if the image of the Eiffel Tower means anything to you, but in terms of weight, this is 3.5 times the Eiffel Tower. And this is 30 meters in diameter, that is 100 yards, 30 meters in height, and 23,000 metric tons, so that's 46,000 pounds. This is what the site looked like in 2010 when the works started, and this is what we are aiming at a few years from now. So next, I'm going to show you a video to explain what fusion is and what tokamak is and what we are trying to achieve here.
With one proton, one neutron, and tritium with one proton and two neutrons. So they collide with a very high energy and temperature around 150 million degrees, which is 10 times higher temperature than in the center of the sun. And they can fuse. So we have helium element and we have one neutron. So this is the most important part of the reaction because neutron takes 80% of all energy of the fusion reaction.
Over the development of the past decades, two concepts have basically survived this Darwinistic process, and that's the tokamak and the stellarator. And both have in common that the magnetic field is ring-shaped. But there are subtle differences between tokamak and stellarator, not just the name.
Now, tokamak is a Russian word, and essentially it just means a donut. That is not exactly what Russian donut is, but tokamak is essentially a donut-shaped chamber.
So a tokamak is a Russian acronym, and means just in Russian language toroidal chamber and magnet. So it's very, very straightforward, and so it has nothing to do with the tokamak. Never confuse that.
It turns out we need strong magnetic fields. So we actually need two types of magnetic fields. The first one happens in what we call the toroidal directions. It's following the shape of the torus around. But that wouldn't be quite enough to keep it completely confined. So what we do is we actually want a magnetic field as well in what we call the poloidal direction. And that sort of introduces a twist.
The first thing you do is you evacuate that vacuum vessel. You pump it and you get rid of all the gas in it.
Then we starting to charge our magnetic system around the vacuum chamber.
You put a tiny amount of postage stamp worth of fuel, you inject that in multiple areas.
And then you switch on a solenoid which is in the middle of the tokamak. And this, by the magic of physics, creates an electric field in the donut.
The hydrogen gas, deuterium and tritium start swirling around inside the tokamak. Then our first heating system kicks on and it zaps this gas into a plasma and the whole thing starts swirling around the tokamak.
So then you use the RF heating systems and another heating system called neutral beam. You fire beams of particles and that gets you from a sort of 1 to 10 million degrees up to the 100, 150 million degrees.
And then the process of fusion starts. The particles can knock each other sufficiently fast so they fuse, and then they produce energy. Then you have lit a sun inside your cage.
All right. So I hope this gave you a little view on what we do. So as it was said, fusion exists everywhere in the universe. It's the energy source of the sun and the stars. It's the source of light, heat, and life on Earth, basically. So in space, this is induced by gravitational forces. When we try to recreate that on Earth, we need magnetic confinement fusion. In fact, there are other types of fusion. The US has developed a laser type of fusion, but the most efficient one so far are the magnetic confinement fusion. So as it was said in the video, we take deuterium and tritium, which are basically hydrogen molecules. When they fuse together, they release helium and neutrons and massive amounts of energy that can be used, of course, to warm water, for example. But this requires a precisely shaped and controlled magnetic field. It requires very high temperatures, so 150 million degrees Celsius, that's 270 million degrees Fahrenheit. And in the end, what we want to achieve at ITER is a burning plasma, meaning a self-heating plasma that would no longer require an external source of heating. So fusion R&D started many, many years ago. I mentioned in the US, they have the inertial confinement studies. We had some in France as well. Wendelstein 7X is a stellarator in Germany. Here you have examples of smaller tokamaks also developed in the US and in the UK. How does it work? You saw the machine here, so I'm just showing the tokamak machine itself. Of course, it's part of a very large construction site. We inject deuterium and tritium gas. We inject electrical current to convert the gas to plasma, electromagnetic waves, high energy neutral particles, and with all these, we want to induce fusion atoms colliding together. The challenge here is to contain and shape the plasma so that the plasma is levitating and not touching the sides of the vacuum chamber. And this is why we actually need all these magnets, just to keep the plasma in shape. Size does matter in fusion. So the ratio of output thermal power depends on magnetic field strength, plasma density, and plasma volume. So you see here two examples and ITER on the right side of tokamak devices that have been built. Tor Supra is in France, JET is in the UK, and what we are trying to achieve at ITER is the largest tokamak ever built. We are also trying to achieve at ITER the first tokamak that will ever have a positive ratio. So far, all the fusion have had ratios than 1, and here we want to achieve the ratio of 10. So 10 times the power we put in to have at the exit. A bit of history on the ITER project, because I think it's important, it's collaborative. It all started in 1985 at the Superpower Summit in Geneva. You see Ronald Reagan and Mikhail Gorbachev. They first had the idea to work jointly on an international project to work on fusion. The ITER agreement was finally signed in 2006 after all phases of design. In 2010, the earthwork started, and here is an aerial view of the site today. So it's an integrated project, an international one. It's funded by 35 countries, so the EU plus 6 other members. You have them here, so China, India, Japan, South Korea, Russia, and the US. Generally, the members contribute in kind, meaning that they provide components. They don't necessarily provide money. Europe contributes the most because we are hosting the project, and then each member is about 9%. Which means that the members are providing the components, and so they are also learning how to make these high-tech components. So this is a schematic view of the tokamak. So just an example, the central solenoid that we saw in the video is provided by the US domestic agency. It will be the single largest magnet in the world. Then you have the orange toroidal field magnets, D-shaped. They are provided by Europe and Japan. And then we have the 6 poloidal field magnets, the circle ones, pink ones here, provided by Europe, Russia, and China. We take a step back. You have here other components provided by other entities. Just have a look at the cryostat building, this massive metallic can all around the tokamak. This is provided by India. You'll see a few pictures of that later. So in total, the tokamak itself has over 1 million components in various shapes, sizes, but generally very big components. So this is a view of the site. All I showed you in the previous slides, so the tokamak itself is just this yellow circle here. All the rest is a bit of conventional stuff, power supply and then cooling towers and so on, and some more sophisticated stuff for cryogenics plant, for example. The superconducting magnets are cooled at 4 Kelvin, so that's why we need liquid helium to cool the whole thing. We have also, because ITER is an experimental reactor, we have massive amount of diagnostic systems because we want to learn on ITER so that someday this can become something more industrial. So a few pictures now, just so you can appreciate the magnitude of the components. This is the cryostat base. So this is the bottom part of this huge metallic can that I showed you before. This is the single heaviest component on the tokamak. It's 1,350 ton. It was lifted inside the tokamak pit in May 2020. So you can see here basically the piece traveling its way towards the end of the picture here in the tokamak pit. That's the moment where the cryostat base is landing inside the pit with the 4-hook crane, and it was landed with 3 millimeter tolerance, so that's 0.1 inch, I think. This is the next element. Just after the base, we had the cryostat cylinder. So you see the size of the tiny little humans at the bottom, so you can appreciate also the size of the components and the precision with which we have to land. This is a view inside the machine. So here many more components have been installed, and the circle we see in the middle is poloidal field guard number 6. And just after we have his big brother, the number 5, that goes above, and there are 4 more of them. This is the central solenoid subassembly ongoing. So I told you before, this is supplied by the US domestic agency. It will be the largest magnet in the world. So in total, there will be 6 modules stacked up to reach 20-meter height. On the left side, we see only 1 module. There is an assembly platform and just 1 module. And on the right side, in pink, you see the next module being prepared to be lifted on top. So of course, we lift on top, and then there are plenty of superconducting joints to be made between the modules. Once the 6 modules will be stacked up, then we will lift the whole tower inside the tokamak peak as one piece. This is a vacuum vessel, so the chamber where the plasma is levitating is made of these components. There are 9 of them that will be welded together in situ. So we see here one piece, but before that we can lift it into the pit, we need to cover this steel element with magnets and with thermal shield. So what we see here is the thermal shield. It's shiny because it's silver coated, sorry. So we basically cover the vacuum vessel with the thermal shield, and on top of that we need to add 2 toroidal D-shaped magnets around it. So that's one of them. It's in horizontal position. We append it vertically, and then we dress it up onto the vacuum vessel. Once we have the vacuum vessel plus thermal shield plus the 2 TF coils, we have what we call a sector module, and this is actually the first sector module that was assembled and on its way to be lifted to the pit. So you can appreciate that the rigging configuration is quite complex, and the lift also is quite complex because here we have 2 independent centers of gravity for the components, and the clearances you see are also very tight. And that's the moment it lands inside the tokamak pit, and we have to redo that 9 times just to have the chamber. Then we still need to assemble more magnets. Okay, so with all this, if you can click on the picture, I'm going to try and explain now why we need 4D planning. So when I studied 4D planning in school, I thought it was just to get nice videos, and it's actually one of the purposes here. We can create an animation demonstrating major project milestones. It's visually engaging, it's easy to understand. The video rendering is very good. We see it's shiny, it can be colored, and basically this is used mostly for communication purposes. This is a research project, it's funded, it's a public project, so the communications team need this kind of advertisement. So this is basically the component I showed you before, and the moment it lands in the pit. But we also use 4D planning for real planning work and sequencing work. So here we see an accelerated view of the sequence of installation in pit. Remember that we have never ever built such a large tokamak in the world. Remember that every piece, no matter how small it looks, weighs hundreds of kilos. So we really have to be really careful how we assemble things in what order, and we need to make sure that we can still continue assembling things without blocking our way. We need to make sure also that we can bring things in with the appropriate tooling. So we do all this with 4D planning on a weekly basis. This is shared with all the stakeholders, the construction managers, the schedulers, and we can get very good feedback to validate the sequencing before it's actually done. We also use the 4D planning to look a bit at the logistics. So what you see here is a temporary building. It's so-called assembly hall. This is where we assemble the pieces before bringing them in situ. And here we are validating also the sequence and making sure that by bringing components in, components that are massive in size, we are not blocking the next steps. So we identify clashes in the sequence, we validate the space available in the assembly hall. We are really, really struggling with space on site. And we optimize the sequences whenever it's possible. And with this, we have improved coordination, and we can anticipate clashes and work on that. These are 2 examples on how we used this 4D to identify clashes. So you see we can model the cranes with their exact distance between them. We can visually see the clash highlighted by the red arrows here, and we can see when the schedule won't happen because of these clashes. Another example that we worked on is looking at the long-term access strategy. Basically, the tokamak building, the tokamak pit, will be crowded with components in a few years from now. And so we've tried to look at the long-term strategy and to look at how we can optimize accesses through the components. Because to get access inside the vessel, you need to pass through these openings, these ports. And with the 4D studies, we were able to go long in term and plan a whole sequence of access. So that's the use of 4D planning, and I can say that we really use it on a weekly basis with all our teams. The next thing I wanted to illustrate, but this was presented also by Keely before in the Bechtel presentation, is photogrammetry. So I think she's made the point, so I will only repeat what she said. We have these drones, we use them, we send them to site. So of course there is a portion of outside sending and having a nice view of site, but here is a video so you can just see the rendering that we can have and the precision that we can have with the drone. So here we send the drone inside the building and we just took a video, but of course you could navigate through the model with your mouse. And you can go on site, you can visualize things, you can measure things very accurately. And this is important for us because then it can help us to calculate the trajectories of these very big components. So this is an example in the assembly hall, as I showed you. You can calculate anything you want. And this is kind of the same, but in the tokamak pit, just so you see. So here we are at the highest level of the tokamak, but you can zoom in and go inside and really see. So on site, we don't use it for progress measurement, but I can well imagine that on a very large construction site, or if you have to make roof inspections at height, you can send a drone and have a real good image, good quality, and be able to do inspections. Okay. That's it. So I gave you a bit of information about fusion, a long-term option for abundant energy. You saw ITER, the thermonuclear experimental reactor, and a bit of 4D planning and photogrammetry to support construction. Thank you.
That was great. Thank you very much. I won't share quite how much of that went over my head. Very impressive. And one of the things I wanted to ask you about was, so 35 different countries kind of involved in this project. Was there an issue with kind of people from different countries coming with kind of different experiences of tech and how they thought that they should be using the tech? And if so, how did you guys kind of work that out?
Yeah, ITER is very multinational. If you go on the website, there is a map showing the origin of the people, and basically it's from all over the world, which I think is really exciting. For sure, we need to accommodate to the cultures. It's different. Also, the components are delivered by different countries, so sometimes it's difficult to align everyone. But basically, when we come to site, it's a funnel. So basically, when you have to put the piece in the pit, there is only one way, and we try to structure the organization so that we are all towards that goal, regardless. So in the end, sometimes it's a challenge, especially for communication, but we are here all for the same goal, and so in the end, it works fine.
I just have one more kind of quick question. The first part of it, I think I know the answer to. So how impossible would this project have been, 10 or 15 years ago or whatever, without using the tech? And kind of going forwards as the project carries on, do you kind of think you're going to be kind of implementing any kind of new tech, or kind of might that evolve a little bit?
I hope so. From my side, I'm only involved in construction, but for example, there are a lot of things being developed on remote handling, especially because we want to plan the whole maintenance systems that will enable to go inside the chamber and do maintenance. So they are using, virtual vision so that you can plan this remote handling system. So I see only the thing about ITER is that you know only 1% of everything being done on the project. You have no idea. The best scientists are there, and they are imagining stuff that you wouldn't imagine. So I'm sure in the future there will be more. Yes.
Okay, perfect. Thank you. Do we have any questions? Does anybody want to raise their hand? Yes, the gentleman over here. Thank you.
Just a practical question. How do you actually transform? What's the process of transforming that super energy into something that's practically usable in the grid?
So ITER is not meant to deliver power, but then it's like a normal reactor, a nuclear reactor. So you get the heat, you warm water, water will be steam, steam will turn into generation, that's it. ITER is only meant to be experimental, but the next step to ITER is called demo. It's already planned. It will be, they say, the industrial version of ITER, and it's already planned, and it will be in Japan. So everything we learn on ITER, and there are things that we hope will work, but we are not sure. If they work, then they will be redone and improved on demo, and demo should be the first industrial prototype to produce electricity in the future. Fingers crossed.
Okay, yeah, question over there.
What's the overall project value on this? And then my next question leading into that is, I know recently here in the United States, Plant Vogtle just came online and has dealt with massive cost overruns. Are you guys seeing the same kind of cost overruns as Plant Vogtle?
So I'm not familiar with the plant you mentioned, but yeah, so difficult question. I think to answer straight, I think at the moment the planned cost for the construction phase, not operations or anything, is 20 billion. We had lots of delays with COVID, and honestly, we also had some issues with components that are currently being repaired. So due to these two events, there will be a new baseline issued end of this year that everyone is working on. It will extend the schedule, therefore it will extend the cost, but I'm not able to tell you by how much yet. That's the next joker question. So again, with the new baseline, the new date will be communicated. ITER is a phased approach because we first want to do a simple plasma just to check it works. Then we want to implement other systems gradually and then have it work. So the first main milestone is the first plasma. In 2016, they had planned to complete it by 2025. We know that it's no longer possible. And let's say that the new baseline will tell us when this first plasma is. But in any case, to have the full testing of everything that ITER wants to check, I mentioned the ratio of 10, but there are also other technologies that need to be validated through ITER. It will be several decades. Yeah, the target of all this is to have fusion reactors, but I don't think from an industrial perspective it will be in this century. On an industrial basis, it will be next year. It's really R&D things here.
Okay, perfect. Thank you so much. Let's give her a warm thank you. Otherwise, nobody's clapping.